Hello everyone, this is Dr. Saeed Mousa. Today I'm going to present for you about our study for the fracture behavior of cracked small bunch test specimen made of epoxy reinforced by hybrid nanoparticles. This study is presented to you by Dr. Saeed Mousa, me, Prof. Amr Abd-Elhady and Prof. Hassam Sallam. This presentation for the IGF 26, which will be held on 26th to 28th of May in 2021. Presentation, we are trying to introduce some of the motivation behind this work, the main two objectives of this study, also the materials that had been used in this study, and how we employed the small bunch test. Also, we'll get some of the result and discuss such kind of result. Finally, we'll try to do or draw some of the conclusion that can be drawn from this study. So, for the introduction, the epoxy resin containing more than one compound belonging to the category of the thermosetting resin have multiple specifications including adhesion strength, chemical stability, and electrical insulation. Also, because of these characteristics, these resin have been used widely as matrices in numerous applications, and the adding of nanoparticle such as nanoceramic, nanowire, carbon nanotube, and the graphene structure to epoxy resin lead to an increase in desired mechanical properties. Also, because of the crack binning and plastic void growth, which arise from the reinforcing the epoxy with nanoceramic, the adding of nanoparticles contribution to the increase of the composite toughness. Also, some of the researchers have noted that a nanoparticle size that has a higher ratio of surface area to volume than that of the large sized particle makes nano size distinguish of the physical network structure. These characteristics are reflected as advantage in increase the resistance of the composites, also including the nanoparticles of wearing rate compared to the large particle, and this type of nanoparticle can yield a layer of strong film and that blend with a wear debris or other kind of the mechanical properties. Also, various evaluation for the various evaluation technique were used to evaluate the tensile properties. Also, we can tell that the tensile properties, flexible properties, and tribological properties for such composites using the conventional technique. But however, nowadays the small bunch test is used to evaluate the mechanical properties for various kinds of composites, especially metal matrix composite, also and the polymer matrix composite. So, the small bunch test is a technique used to evaluate the mechanical behavior of the miniaturized thin disk. Also, the use of the small bunch test has emerged as a potentially useful technique for mechanical characterization using the small specimen. Therefore, one of the main objectives of the present work is to ensure that the accuracy of the result obtained by the small bunch test and comparing them with the result obtained from the diametral tensile testing. So, the main objective in this study is about the small bunch test was adopted to measure the tensile properties of the present nanocomposite, and the second main objective is the effect of the presence of the pre-notch with different three-notch geometry, the single edge notch, which is the SEN, straight bottom notch, the SPN, and circular bottom notch, which is the CPN, on the small bunch specimen have been studied both numerically, we did it numerically, and we did it experimentally. So, for the materials, a composite material containing a commercial resin that we got and the hardener with additive nanoparticle. Also, to achieve the complete hardening of the epoxy, we got a 12% hardener was used, which was described by the manufacturer. Also, before adding the hardener, however, adding the nanoparticle types with various percentage were thoroughly mixed in the solution. So in this study, aluminum oxide and silicon carbide nanoparticle were selected as a nanoparticle additive. These were purchased from an international group in China. Also, the size of the shape and the shape of the nanoparticle chosen for use have an average spherical diameter around 50 nanometer, and the physical and mechanical properties that can be seen here for the aluminum oxide and the silicon carbide, and they are very closed. I mean, for the tensile, for the fracture toughness, and for the hardness. Somehow there is a big difference here, but still for the fracture toughness, the tensile strength, and we can tell from our experimental and our numerical the difference between those two materials. Also, for preparation of the nanoparticles with the reinforced, I mean the epoxy with reinforced nanoparticles, the nanoparticles were mixed with the epoxy resin by using silicator. And adding our papers or the reference in the end of this presentation, because we do want to spend more time about how we prepare those samples, because we have more than 4 or 5 studies in this one. So the nanoparticles were mixed with the epoxy resin by using the silicator apparatus with a frequency of 40 kilohertz, and the mixture was placed in the silicator apparatus at a temperature of around 40 degree for 2 hours to disperse the nanoparticle in the resin. Subsequently, a 12% of the hardener was adopted to the mixture. This was added with a gentle mechanical steering to ensure a uniform mixing and to avoid any formation of bubbles. After that, the mixture was poured into a foam mold, and the mold geometry and the weight percentage of the additive were changed according to the test time, as discussed in the coming slides. So, uh, let me tell you about the small bunch test. So, the small bunch tests that we use in this study were carried out using an experimental device like this one shown in this figure. This device was custom and designed in our lab, and it was mounted in a universal testing machine fitted with a 20 kilonewton load cell. The diameter of the small bunch tested specimen, which is around 20 millimeter, and with a thickness of around 2 millimeter. Also, the small bunch test in the present or in this work is used to describe the effect of the nanoparticle weight percentage for the aluminum oxide. It started from 0.5 percentage from the weight, 1.5 and 3 3 percentage of the weight, and the stiffness of the composite specimen. Also, we are trying to extract the load displacement curve for this, I mean, small bunch test. Okay, here I'm trying to show you what we have done in the small bunch test for this study. So here in this figure, we are showing the experimental for the small bunch test deflection curve, which is showing here in the left one for the A, the load versus the displacement, and we can tell here the material that are no additive, 0.5 percentage, 1.5 and 3 percentage for the additive. And in this one curve we can tell that how we I mean the behavior of those curves, how it should be looked like, starting from this one, as you can tell. I mean the top one here, let me put the mouse here, this one here, how it is looks like, and the other one is about the I mean the other one, how it is the behavior, how it is working. And we can tell there are significant pop in for the additives for the material. The maximum one without no additive, it can be tell here. Also, I'm trying to do the pointer. Okay. Also, I'm trying to show you here how it is looks like for the for the small bunch test. There are 4 region: elastic region, elastic plastic region, and the stretching, and finally the failure. And we can tell here all the sample that have any additive in the reinforced epoxy, it are all following the same behavior, while the other one it has only no elastic plastic region. Also in this one, I'm trying to see here, is the other one, which is about the for the maximum value load deflection in this curve. In this curve, it's seen that in for the B, here, it is seen that the maximum small bunch test force decrease with increasing the weight percentage of the nanoparticles, and the sample without additive show more resistance when compared to other reinforced sample. For the elastic stage of the small bunch test curve, as shown in figure 13a, the reinforced sample have less stiffness compared to the unreinforced sample. Furthermore, the second slide, we are trying to compute the modulus of elasticity E of the specimen, and that can be estimated by using the value of the slope of the elastic region in the small bunch test load displacement curve, which can be by other study. And it follows the empirical correlation between the small bunch test experimental result and the E. And there are equation in one of our extracted empirical equation that we get from our one of our study, and we correlate the factor computed by using the modulus of elasticity of the epoxy, which is around 3.7 gigapascal, and we see here the value of the Young's modulus of the samples, and we can tell here that from figure B, that's the scene that the modulus of elasticity decreased by using the nanoparticles of the aluminum oxide. So here in this case, in this one, the second objective of our study is to get the stress distribution around the crack front of the three different crack geometry. We have the single edge notch, and we got the straight bottom notch, and we got the circular bottom notch. I'm trying to get the time, it's around 12 minutes. So in this one, we try to the distribution of the normal accessories is not uniform near the notch root in the case of the single edge, and we can tell in this one. Also and the straight bottom notch for the SPN as well, and the other study it used the straight bottom notch, which is the SPN is a plate sample, to determine the crack initiation, and they found that the maximum stress located beside the small bunch assessment is the stress and the strain distribution around the notch root is not uniform, which confirm with our present result. Also, furthermore, the upper half of the SEN, we can tell here, the upper half of the SEN, which is in the second one, we got the upper surface and in the bottom surface for all different kind of ratio. The upper half of the SCN surface is subjected to compressive stress. In the case of the CPN, which is the circular bottom notch, the three normal stresses, the sigma RR, the sigma theta theta, and the sigma ZZ, are uniformly distribution around the notch root. Therefore, the CPN is a suitable geometry for the steady and uniform crack and uniform crack growth. And to study the notch of the sensitivity of the three different notch geometry, we got the XFEM was adopted to predict the site of the crack initiating and the path of the crack growth for a smooth and pre-cracked specimen, and that can be shown in this figure. And in this figure, the site of the crack initiating and the path of the crack in SCN specimen with notch depth in a specimen diameter range from 0, which is the smooth, up to the range from A to the D, 0.6, and for the AD lower than 0.4, the notch sensitivity was observed. However, for the A and D, the range from 0.4 to 0.6, the crack emitted from the notch root, but there are other crack emitted from the smooth surface near the notch in this figure. So, this is agreement with other result for the G integral and the crack opening displacement. Also, it is worth noting that the final failure is not affected by the presence of the SCN. The shape of the final failure is a circular shape. Also, in the case of the SPN specimen with notch depth specimen thickness ratio A to the equal to the size of the crack initiation and the path growing crack mainly depending on the center of the deformation of the specimen, ignoring the presence of the SPN as we can see in this figure. And the finding is obtained by others studied and supported the present observation. Also, we got here in the same observation was found for the CPN specimen with A to the T ratio zero point 0.2, and by increasing the A to the ratio from 2.5 to the crack emitted from the notch root, it can be concluded that the sensitivity of the CPN is dependent and in AT and in the ratio of the circumference of the circular notch to that of the loading ball. In general, we can see the failure mode of the pre-cracked small bunch test specimen is a typical failure of a smooth small bunch test specimen regardless of the crack geometry. Uh, Here we try to get some of the conclusion. For the main objective, the addition of the 2 percentage of the aluminum oxide nanoparticles to epoxy resin was found to be the optimum ratio in the present work. Also, to generalize the small batch test, the I mean, sigma b, I mean the material dependent empirical constant can be predicted by equating the tensile strength measured from the small batch test and the indirect tension test. For the second main objective, we can see that the circular bottom notch specimen is a suitable candidate to determine the fracture toughness of the material due to its position coincide with the failure location or two of the small bunch test specimen. Finally, the sensitivity of the circular bottom notch is dependent on the A to the T ratio, which is the crack length and the thickness, and the ratio of the circumferential of the circular notch to that of the loading ball. Those are the references for our study that have been concluded those of this presentation. Sorry for being rushing, and hopefully to see you all online for the presentation, and we are open to any discussion or question that we can get, and thank you very much.